Welcome to the Cave of Geometry. In contrast to the prisoners in Plato's cave, who could learn about the real world only by passively watching its shadows on the walls of their cave, we can move about the familiar and the unfamiliar geometries of space. Our little play is in 5 acts, each telling a different story of space. It was presented in the Cave Virtual Reality Theater in the V Room at SIGGRAPH 94 in Orlando, Florida. Here we are still in Euclidean space, where we learn to fly about a familiar shape, the SIGGRAPH 94 logo seashell, which changes its shape by a homotopy to the cave horn. We next enter hyperbolic space. Since we cannot observe space directly, we must populate it with objects we can see. This is a tessellation of hyperbolic space with 927 right-angled dodecahedra. Imagine your surprise if, while groping along the walls of a dark room, starting at a right-angled corner and continuing to the next corner, you did not return to the original corner after the 4th leg. Instead of a square room with 6 walls, you find yourself in a square room with 12 pentagonal, but still right-angled walls. Compared to Euclidean space, hyperbolic space has more room for things further away, where big things subtend smaller and smaller visual angles. Each of those apparent disks you see are entire hyperbolic planes, tessellated by right-angled pentagons. We thank the folks at the Geometry Center, Stuart Levy, Tamara Munzner, Mark Phillips, and Charlie Gunn, for helping us with the non-Euclidean spaces. Hyperbolic geometry is the natural geometry for most surfaces and nearly all 3 manifolds, according to Bill Thurston, so it pays to learn all about them. It is easier to see the whole story in 1 dimension lower. This story repeats, so you needn't catch every detail the first time around. The Poincaré model of the hyperbolic plane can be tessellated by octagons. Half the fundamental octagon is ripped away. Each half is rolled up into a torus, the way you'd roll up a wraparound computer screen. Only this torus has a hole, which connects it with the other half, off stage, to form the double torus, a surface of genus 2. The colored triangles are all congruent to each other in the hyperbolic geometry, so applied to this 2 manifold. Our actors here are Blaine Lawson's snails. In reality, they are ruled surfaces in another non-Euclidean geometry, namely the positively curved 3-sphere. We use their conformal projections to our own 3-space to tell a much simpler story about Möbius bands. This way, all surfaces you see in this story are parametrized by the same set of 4 equations. The snail is a Möbius band whose boundary circle lies in a plane. Usually, we think of a Möbius band as a rectangular strip glued end to end after having been given 1/2 twist. Möbius was interested in the surface obtained by shrinking the boundary of such a strip to a point. The resulting Veronese surface was first presented as a computer graphic by Tom Banchoff in 1977. It is a closed but one-sided surface without self-intersections, which can exist only in 4-space. Its shadows in 3-space, Steiner's crosscap and Roman surfaces, do have complicated self-intersections. If we give our band a second-half twist before gluing, its boundary becomes 2 linked circles, showing how to generate the torus in a novel fashion. Giving the ribbon a third half twist, we get a Möbius band with a trefoil knot for its boundary. Stretching its diameters here produces Brame's knot box. This is the surface that we originally wanted to investigate, and built this cave application because it is too difficult to visualize this complicated surface any other way. Finally, we step into the geometry of the three-sphere as we had done earlier for hyperbolic space. The three-sphere is our familiar three-space gathered up at infinity to a single point and given a uniformly positive curvature. It too can be tiled by dodecahedra, but these are not right-angled ones, and only 120 of them fit into this compact space. We demonstrate one curious feature of spherical space. We think of ourselves as standing at the North Pole of the three-sphere and ship identical, equally spaced dodecahedra towards the South Pole. At first, the visual angle of a fleeing solid decreases, and it appears to move away, which it does. Beyond the equator, however, the visual angle increases again, and it appears to be coming back, which it doesn't. It remains behind the nearer, though smaller, dodecahedron. Once such a solid reaches the South Pole, its visual angle fills out all of our field of view, and our entire world, including the cave, is now contained inside this single dodecahedron.